Toybas, am I audible now? I think only you have joined. Please respond. Do you unmute yourself? Hello. Am I audible?
Yes, you are audible and visual.
Do you know who are still want to join? Any information? Only you are there, I think, in the lobby. Lobby is in the session. Do you have any information? Some other are also coming or not? Your friend?
No, I don't have any information, sir.
Okay, okay. Okay, fine. Have you solved this week's assignments, Bas?
Yes, I tried to solve some, but I think maybe somewhere I have some doubts.
Okay, okay. So you can carry with your doubts. I was also solving those problems. That is also my duty. So in between, you keep on asking me. Okay. If you have any problem, keep on asking me. I'll be because this day because today I think no more people I think except you. So you keep on asking. It will be a better interaction. So the rest of the days there is no interaction at all. So I'm quite um, quite unhappy with the performance of the class, and it is not interactive at all. So please interact, Toibas. Interact whenever you have doubt. You raise your hands, and we'll be discussing. Okay, don't hesitate.
Okay.
So so I'm sharing my screen. So my screen is shared, right?
Yes, it's shared, sir.
Yes, yes, my screen is visible to you. Thanks. Okay. Now this lecture 27, which includes, I think I should not wait for others. We'll be starting because we'll be late. The today that four lectures are covered. So one is creep of the concrete. The lecture 27 to creep of the concrete, its recovery, and what are the factors are involving in creep. What are the effects of creep? Okay, and also it's followed by the prediction of the creep. There are many formulas, and also in there's shrinkage also. Actually, with creep, the shrinkage also comes in picture. Okay, so creep means movement of water from gel pores, from one gel pore to another gel pore. However, the shrinkage is the getting water out of the gel pores is the shrinkage, main philosophy of the shrinkage. And when there is a decrease in volume. When the decrease in volume, it from the actual one, the original one, then it contract, the volume contract, and the cracks started to appear, propagate. So that is the main fund of the shrinkage. And later on there is a secondary creep. There are various type of creep also mentioned. Actually, it is the lecture also discussed the creep and shrinkage simultaneously. Okay, afterward it is mainly focused on the shrinkage of the concrete, its effects. The same way it is discussed about the creep, and the same way it is discussed about the shrinkage of the concrete. What are the factors that and that shrinkage get affected? The prediction of the drying shrinkage. Okay, and in lecture 30, it is shrinkage is continued, and there are various formulations are there. And okay, and how the capillary get comes in picture, and due to the surface tension, the shrinkage are getting affected. Okay, so this will be understanding one by one. And then first, and see if we have time, then we'll be discussing that MCQ questions in last 10 minutes or 15 minutes. Okay, so I am starting. So actually, the first question was the creep happens in the concrete when the stress are beyond that of the ultimate capacity. Okay, so what is the 30%, 70, 60%? The first question means when the creep started. Okay, when the stress is 30% of the ultimate capacity, when the stress magnitude reaches ultimate capacity means the strength. Okay, 30% of the strength, 60% of the strength, 70% of the strength, or none of this. So actually, the creep is mainly because of the sustained loading. It creep can happen by its own weight also, the by own weight of the structure also, or the sustained loading. If I deduct the structure, if I not include the self weight of the structure, I only rely on the imposed load. Then for the constant imposed loading, the at a certain stage, at a certain time duration, the creep starts to occur. And actually, there are methodology that also accounts this creep. So actually this creep, I am telling you, yes. Yes, actually, one of the measurement in the creep, if you study the lecture, Professor Bhattacharya, then as per the STM standard, STM C20, STM, I'm telling you, yes, ASTM, American standard, is STM C512. C512. Actually, it stacks the cylinder are subjected to sustained loading and strain are measured. Okay, and in simpler way, it is subjected to concentric cylinders, subjected to concentric cylinder to a constant load applied manually through plates. See, these cylinders are there, and this over the platens are there, the load are applied at a constant load. This is constant load over a period of time. Constant load are applied over a period of time, and how the creep is getting occurred. So creep means this is deformation. Okay, deformation. This is deformation. Okay, after deformation. After certain deformation, it get compressed. So this is the section of the. So actually, the load is measured using a calibrated steel tube. Actually, this load is measured in calibrated steel tube. This is called the dynamometer, and at 20 to 30% of the strength. And actually, when the stress level reaches to 20 to 30% of the strength, it started to measure. So and the gauge, actually the strain gauges started to measure the deformation. Okay, actually the thing is this, there is a small setup. I just want to show you. This is the cylinder. Actually, this is the setup where this is the piston. This is the piston, and this is the piston, and here the nut is there. Here nut is there. Nut is there, and here the concrete. Here the concrete cubes. This is the concrete cylinder. This is a concrete cylinder. This one after another, the concrete cylinder are placed. Okay, these concrete cylinders are there. Which cylinders are there? Actually, it is a front view. I'm saying a front view. Actually, it is a 3D view. 3D view. It's a four rods are there. Okay, four rods. This is the okay. It's like this. So the concrete blocks are inside this. This is the piston. So this way you can imagine. So is piston is getting a thrust to that, and how the concrete getting deformed is it's gauged by the strain gauges. So these are the nuts. These are the nuts, and the pressure or the stress maintained. When stress maintained 20 to 30% of ultimate strength. Ultimate strength. Ultimate strength. However, there is also things that the creep Actually, there's also one curve also there. If you see the curve where I will also discuss in few minutes. This strain and versus time curve is there. Time is there where this is the T naught where the stress is applied. The stress is suddenly the stress is applied. This elastic strain is there. Elastic strain means the strain is recoverable after a certain period of time. It is continued. The sustained loading is get continued. Then the strain will be non-linear. When there is non-linear, it will be inelastic strain. So it will not get returned to its original form. So this curve is segmentized with the three categories: the primary creeping, creep, primary creep, secondary creep, and the tertiary creep. Okay, tertiary, tertiary creep, tertiary creep. Okay, tertiary creep, and ultimately it leads to failure. Okay, if it is it in a certain time, certain period, after a certain period of time, it will fail. Okay, however, during the creep, it is seldom that the concrete or the structure get failed. But if it is a long duration, the loading is much higher, and there are other factors also coming picture that also affects the creep. That is the temperature. Okay, so that magnitude of the load is getting increased. So it is also leads to failure. It can also leads to failure. So these three stages that can be observed at the st at the stress at stress 60% to 70% of the strength. So these are the theory, and based on the theory, these values are derived or are discussed. So actually, this values refers to the actually the first values is the test process where this stress level is maintained. However, after the stress after experiment is done, these two stages are found at 60 to 70%. So at each and every theory, there are different stress level under which results or which trigger the creep. When after with the test level the script get started, and actually in actual case with the self weight itself, if you don't load apply in load with the self weight, there's also possibility of the creep get occurred. Okay, so it is a heavy mass concrete structure. So actually there is no such stipulated thing. There is no such fixed percentage of stress. So actually it is none of this. So the first question is the creep happens in concrete when stress are beyond that ultimate stress, ultimate capacity. Actually it is none of this. It's none of this. Okay, now the second question is the assertion is the statement is the concrete shows less creep after removal of the water from it. Yes, actually, if you observe, actually these two things are there. One is evaporable water, and is the another thing is the water that the structural water or the already poor water. Okay, so one thing is evaporable water, one thing is poor water, and it has been studied that with the evaporable water, because the evaporable water it is at the it remains at the surface of the concrete. Okay, so when it get heated with a smaller temperature, differential temperature, it get evaporated, and it shows that after if you remove the evaporable water somehow by mechanically you remove the evaporable water, there is less creep. However, it is a contradiction to the main theory that when actually that creep mechanism, actually the creep mechanism the creep mechanism involves the yes, the creep mechanism. There is no robust theory or no standard theory that defines the creep, the reason behind the creep. However, there is a theory still available which accounts this. Uh, yes. Yes, which accounts this creep is due to the water, when the water moves from one gel port to another gel port, movement of water. If the movement of water is there from one port to another gel port, see one where the density of water, the density of water is much higher, the pressure is much higher. On another side, this concrete structure, the pressure is much lower. Then it will move from, it will capillary or something else, the force, it moves from one port to another port. Then this movement leads to the creep. Okay, leads to the creep. So it leads to the creep, and creep occurs at all stress level within the surface strain and linearly dependent on the stress when the pore water content is constant. Okay, so there is no pore water, there is a constant pore water pressure is there, then the creep occurs. And okay, so that way it applies to gel ports actually. The creep is associated with the gel ports. However, in contrary, this evaporable water is different. It is studied that with the if you remove the evaporable water from the concrete, then this creep is less. However, if you consider this water, the structural water or the gel water, if we move from one place to another place, then it shows the creep. It shows the more water is moving to one port to another port, then more is creep is there. So this assertion is correct, but there is the two theory. If you have to keep in mind. Okay, so the reason is the creep in the concrete is related to the movement of the adsorbed layer. Yeah, yes. Yes, the creep is the movement of the adsorbed or adsorbed or interlayer water from larger to narrower pores. Yes, it is also a correct statement. It's also due to the movement. This creep also occur. If the movement is, there is a saturation, there is a dry, when there is a wet condition, the creep is less compared to the dry situation. Okay, the dry situation creep is more and the wet situation creep is less. Okay. No, so you have to be very specific. When there is evaporable water, then by observation the first statement is correct. However, as per the theory, the second statement correct. So assertion and reason are true, but they are not the reason is not the correct explanation to the assertion. The statement stated as stated below, as stated. Okay, so now the thing is two things. I think I'm able to show the reason why these things. These are the factors behind the uh, two phenomena. Okay, so okay, then it will be the creep relaxation is also there and creep recovery also. So I'll come to that thing one by one. Okay, and three is the so I think this assertion is correct. Assertion and reason are true. Assertion and what are the reason and statement reason is mentioned is true. Is true. However, reason is not the correct explanation to the reason is not the correct explanation. Correct explanation to the assertion. The assertion. Okay. So now the third is the The third is the matching things. So actually, the factors affecting the creep and the effect of the creep. How it the factors affecting the creep. Okay, so yes. So actually, first is the factor affecting the this is the elastic modulus, of the aggregate. Okay, so let me just put on the fan. I'm getting this heat hot and it's one day today. Thank you for your patience. So, the factors affecting the curing conditions, all the things are there. Okay, so the factors, what are the factors affecting? The factors affecting, yes, the factors affecting the creep. Second one is the E aggregate. Aggregate, Young's modulus of the aggregate, the steepness of the aggregate. More the steepness, lesser the creep. So this affect the creep in this fashion. Or this is the curve. The creep is there, the creep strain. The creep strain is there, and this is the E aggregate. Okay, aggregate. So let's have the aggregate, this steepness value. And the higher the steepness value of the aggregate, lesser the creep. Okay. Okay. So, and in another way, you can identify this effect of the this E value. Actually, mainly key and cement paste. Actually, the cement paste is very much sensitive for the creep. More the cement paste, actually, the more the creep. Actually, okay. So in the cement is in plastic state, remains in plastic state for the fresh concrete. However, in the fresh concrete, this or the in hardened state also, this aggregate is solid. So when the solid is coming, this actually the E of the aggregate is much higher than the cement paste. Whenever the creep in the cement paste, the creep means the deformation. Actually, either in compression or in tension. So whenever there is a tension, when there is a tension in the that is cement paste, then it is also get attached to the aggregate. You can think in your own way how the this aggregate comes in picture, how the elastic modulus of aggregate comes in picture. Okay, so whenever the paste is there and whenever there is a tension or compression is happening due to the creep, to sustained loading, I consider the tension. Okay, so the tension is occurring, and as because there is it is a total, the total body that combines this aggregate along with the paste, and it is the bonded is very strong. If we consider the bond is very strong, then this is the aggregate, and this is the cement paste, and somehow the cement paste is getting tensile stress with the creep. However, it also try to impose stresses on the aggregate. However, because of the E value of the aggregate is very high compared to the paste, it also it gives restraint to the cement paste to get deformed. So it will also give the negative force. It also give the reverse force. So that's why the ultimate that effect of the creep get nullified, or the effect of the creep get reduced. In this way, this E value is affecting the creep. This way you can understand. Better to just to memorize all the thing, and um, go through these things. If you think in a logical way, then it's also uh, beneficial for you. So now the second point is the second point is W water cement ratio. Actually, the water cement ratio, if more water cement ratio is there, higher the water cement ratio, higher will be the creep. Higher will be, more will be the creep. Actually, water cement ratio means water cement ratio is more. What is distribution means the water is also is more. If I consider the water is more from is the water is more than from one place, one gel port to another gel port, water is moving at large, then the sustained loading, then it also have possibility that it deforms more under same stress level. Okay, at a particular age, a particular certain time, a certain duration, after a certain duration, it deforms. It happens because of the water from moving from one gel put to another gel. Now it is curing condition. Curing condition is there. How you are conditioning. Curing condition is there. So curing condition means this if you curing if you the curing is sufficiently if you're curing this is sufficient time duration it is getting cured, then this uh, the, that hydration process will be better. A more hydration process means a more elastic modulus will be developed. And to me, it also gives to robustness of the concrete and also the creep. There is a restraint to the creep also. Okay, relative humidity. Relative humidity. I'll come. Relative humidity. Humidity. Actually, the relative humidity. If there's a curve also there. Curve also there. 50%. For 70% and 100%. 50% relative humidity, 70% relative humidity, and 100% relative humidity. Okay? So it's 28 days. This age in days. Okay, and these are the creep coefficient. This is the creep. Okay, so with increase in age, for the 50% relative humidity, the creep is much more. Relative humidity is 50% is for 50% is much more as compared to 70 and 100%. So okay, so actually the derivative humidity means the gel should be more or less saturated. So 50% means 50% means it is saturation, the gel port saturation, the degree of gel port saturation. If I coarsely understand this thing, if you coarsely understand, or if we understand is as a whole, just a layman language, relative humidity is the saturation of the gel ports. So 50% humidity is less saturated than the 70%, 70%, and is saturated for 100% relative humidity. If you consider, then because of the saturation, there is no pressure differential among ports from one location ports to other locations ports. So whenever there is a no pressure differential, so there is no movement from one port to another port. That's why this 100% the 100% we are seeing the least creep as compared to the 50% and 70%. So I think you are getting what I am able to show you the reason behind why the relative or the effect of the relative humidity on the creep. So and now there is a also the volume. It's a aggregate volume. Okay, aggregate volume. The aggregate volume also matter when there is a large volume of aggregate. So actually, it gives the most strength to concrete. However, obviously there's also the paste content. There's sufficient optimum paste content for the good mix design. However, if for the high strength concrete or something, we can use the more aggregate along with some other superstructure. If the aggregate volume is much more, the stiffness will be much. The stiffness will get improved for the concrete, and it's also results in less creep. Okay, also results in less creep. Now it comes this relative humidity is volume to surface area. Yes, it's volume to surface area. It's volume to surface area. Surface area. Actually, this volume to surface area is this thing such that this Yes, actually, this the more surface area is the more evaporation, surface evaporation. So more the surface evaporation means the water will not actually P by S. P by S is more means the surface area is more means surface area is less. Surface area is less, so less evaporation. Okay, so whenever the less evaporation, the creep will be more. So actually, the water is not evaporating. What is not evaporating? So there is a sufficient water that can be transferred from one gel port to another gel port. Okay, so the creep will be much more. However, this volume surface area is less. Means surface area is much more. Is the because of the surface area, larger surface area, the more evaporation is there, and so there is no there is no remaining water movable water that can travel from one capillary to one gel port to another gel port. In certain duration of constant loading, there is no such water. There will be no such water. Then the creep will be less. Okay, the creep. Sorry, and the I think yes is low. Yes, the creep will be higher. Sorry, I'm getting I'm getting I think saying wrong something wrong. Is V by S. V by S is low. V by S is low. Creep will be higher. Yes, that is the, I think I have to change the way I am saying, because it's contradictory. Sometimes it become contradictory because of the evaporable. I am considering the evaporable water. Okay, so it is not at all related to the evaporable water. It is about the gel water. When the surface water is surface area. This is the surface area, specific surface area. Surface area. This surface area is the surface area is more, then there is a possibility of more water to evaporate. So in the surface area is a more water is evaporate, then it will see this is a concrete block and this is the surface area. If I consider, then if it is more, then more water will be passed through from this. However, because of this more water, there's also chance, also the tendency from the uh, other water will go to fill in this place. So there will be movement of water and the creep also it takes place. So creep will be higher. Creep will be higher. However, for the V by S is higher, means this the surface area is much less. So surface area is much more. So there is small evaporation. So and there is this most of all this is saturation is condition is there. So less quantity of water can travel. So creep will be less. The creep will be less. And also there is a fine to aggregate ratio is there. Slump also it happens. Slump is there. Okay, and also fine aggregate to total aggregate ratio, fine aggregate to total aggregate ratio, and air content also there. Air content also there. Okay, so these things are the important pattern and temperature. The temperature is there. Temperature is there. Is there. So more the temperature, the more will be the creep. Okay. So actually in this So, so decrease in first option is the decrease in aggregate modulus of elasticity. The effect of creep increases, and it is showing. So decrease in elastic modulus aggregate. Uh, the, the effect of yes, it is just showing the in reverse way. So it is correct. One is correct. Okay. Yes, because of the decrease. If aggregate elasticity is if decreased, then I will also show you. Is with the lesser value of E, creep will be more. So it is correct. Then the second option is the increase is water cement ratio. Yes, increase higher water cement ratio, more creep. So higher water cement ratio, it is they're showing it's decreasing creep. No, it is wrong. So one is correct, two is wrong. 3 is increase in temperature, increase the creep. Is yes, it is true. 3 is true. 4 is increase in load application age. It decreases. Actually, there's also a certain phenomena that age of the loading if increases, then the creep at the if you also say if you check the IS code, the creep coefficient also getting lowered with the higher days. If, 7 days, 28 days, 65 days. So up with the increase in age, the creep coefficient also getting lowered. In the initially it is just much more, and afterwards it can get reduced. So with that concept in mind, this fourth statement is true. So increase in node application ages, it decreases. Okay. So so the true one statement 1, 3, 4 are true. Okay. I think what there, I think only you. People. Okay. Now this fourth question. The fourth question is the statically indeterminate structure. Yes. Is the statically indeterminate structure. Uh, yes, statement is creep relieves stress concentration. Okay. Actually, statically determinate is, see, this is the hinge condition. This is the, see, this is the hinge condition. This is the support floral condition. So there's a 1 and 2. There's a rejection. There's one reaction. So 3 equilibrium equation, 3 unknowns. It is statically determined. However, if there is a 2 fixed support, the fixed support is there. So 336 is there, and it is about 6, and only 3 equations available. So 3 is a statically indeterminacy. So whenever there is the intent, the more the indeterminacy, more is the stability, or it will be more restraint is there. So in that case, statically indeterminate structure, it says that removal of this creep, um, this structural creep relieves stress concentration. So whenever the creeps is there, the restraint, there will be some relaxation in restraint, and the stress concentration will be removed. So actually, if you see this here, there is a bending moment. So if you, some load is there, bending come like this. So this is the thing. So the whenever the bending moment is there, so according to the bending moment, my by I. So this m dash, it is m dash, it is something m. So okay, second into so this, if we say this negative is positive something, or it is some condition is negative, it is positive. So in the situation, this stress concentration will be more in the restraint. However, the creep will due to the creep, this the stress concentration also get removed, because there's relaxation in the supporting restraint, restraint, restrainment, and reason it is showing that as member are restrained, relaxation, as members are restrained, relaxation happens in turn, which in turn increases the shrinkage stresses. Okay, actually, actually the stress concentration leave the stress concentration is correct. By relaxation, by relaxation, um, by relaxation means, see, the I want to show you some the this relaxation. What is the relaxation means? Yes. So creep relaxation. First of all, I want to remove this one. So creep relaxation. So creep relaxation is nothing but creep relaxation. When the creep relaxation happens. So first of all, this is a pre-stressed. I am just talking about the pre-stressed concrete. I'm not talking about the other type of concrete test treatment or concrete configuration. Properly. This is a concrete block. Here, the pre-stressing bar is there. Pre-stressing bar is there, and here we are giving a compression. Already giving a compression. This is the pre-stressed concrete. Okay, so this is the concrete block. Okay. Now, if we yes, yes, uh, if we see if we see there is a there is a yes, yes, after this is the elastic deformation. This is after elastic deformation, after construction, after elastic deformation, this reduction in length, this is the total length. See this L dash, this small L dash, reduction in length can happen. Okay, this is the this L dash are the elastic deformation. Elastic deformation. Elastic deformation means after removal of the pre-stress, it will come back to its original location. And now what we are doing, we are keep on maintaining this pre-stress. Then the creep will start to appear. So it will gradually the creep will start to appear. It will gradually decrease. The length it will get contract. Okay, so deformation will be much more. Now what we are doing? Now what we are doing? Here we are this elastic information we know, and from and beginning onwards we are providing some restraining mechanism here, restraining mechanism here, restraining mechanism here, so that it will not get contract. It will not get contract after this elastic deformation. So what actually happens? What is happens is, and this is the compression, we are giving the compression, and with the restraint, this restraint mechanism, we are giving restraint. We are giving with the given restrainment or restraining mechanism, applying the restraining mechanism. What happened? It will not get contract further upon the sustained pre-stressing load. Sustained this pre-stressing, pre-stressing. Okay. Sustained pre-stressing load. So it will not get contract further. So actually, in another way, it can be said that it will giving the tension in a tensile force to the concrete. So and thus it neutralizes or some amount of the compressive force. So it is a loss of the pre-stressing. Okay, so the loss of pre-stressing or a lot of the force that has already been provided. So it is called actually it is called a relaxation. Okay, so so this is called a relaxation. However, um, however, by relaxation, by relaxation, this relaxation reduces the shrinkage. Uh, yes, the relaxation happens. Yes, relaxation actually because you see this is the shrink means the volume getting decreased. If you not there is no relaxation. If there is no relaxation, this is the creep because of this is the creep relaxation. We know what is the creep relaxation. That is the main thing. And now if we connect it to the shrinkage part. So whenever there is a compression, if you are not giving any restraint mechanism, not implemented any restraint mechanism, we are keep the deformation allowed for a long duration, then it will get contract, and at a certain point of time there will be crack. There will be crack here and there. because of this volume change. Okay, because of the volume change, it will appear. It is inhibited. However, if we put the restraint mechanism, it will not get contracted, and in return, it reduces the shrinkage stress, reduces the shrinkage, so shrinkage will not appear. However, in the reducing part, it says that it increases the shrinkage stress. So the assertion is assertion is true. However, the reason is false. So fourth question is the assertion is true. This assertion is true. Assertion is true. But however, the reason is false. Reason is because it says that it increases shrinkage, but it actually not reduces shrinkage stress. Okay. So now the fourth question is under the fifth question. The fifth question is said. What it is said? Yes. Which of the following statement is true? Now the first statement is in mass concreting. In mass concreting due to creep. Mass concreting due to creep, there is a possibility of decrease in cracking. So the mass concreting may enhance the cracking possibility by causing more thermal deformation. Actually, what happened in mass concreting, the thickness is much more. See, this is the top surface of the mass concrete. So this is the bottom surface. Okay, so I'm saying this is it's exposed. Okay, so this is the concrete. Concrete is partly this is very thick concrete. This is the mass concrete. Mass concrete. The top surface. Okay, and there is a difference change in thermal temperature. This is a delta T is there. So delta T subjected to differential thermal. It's a differential settlement or differential thermal loading is there. So actually top surface top surface is exposed to exposure environment. So top surface, so maybe this exposed to the environmental temperature. So top surface, if I say this outside, it's a and temperature is maintained something 50 Celsius percentage. So the top surface directly is exposed to 50. However, because of this thickness, the lower surface is not exposed to the temperature. Because of this temperature, uh, this upper surface will try to expand. Upper surface try to expand. However, in lower surface, it will not. It will not get expanded. It will not get expanded. So it will try to restrain the expansion of the top surface, so it will give the some compression here. So the top surface is getting compressed. So because of the thermal differential in thermal change, so this phenomena can happen. So in mass concreting, the uh, enhance the this is because of this difference in deformation. Okay, or deformation, this crack can occur. So crack can occur may enhance the cracking possibility due to the thermal deformation under temperature differential. This is a temperature differential. Yeah, correct. So temperature is higher and heat dissipation occurs at the top surface. In the top surface, the heat distribution is much more. Okay, so heat distribution is much more and much more. Now the bottom surface remain 1 mark. Actually, in another way, I can say I'm just showing that I'm not considering the dissipation. If I consider the dissipation, then it's also get another way. It can and in another direction it can also get confirmed the phenomena how it is the cracking get occurred when the top surface is exposed to exposure and there is a the first dissipation. See, this is the 50 degrees Celsius temperature or something maintained is here. Inside the concrete is 50 degrees Celsius temperature. So I'm not considering the outside temperature. And it is exposed to the, now it is exposed to the environment. Now what happened? The top surface will dissipate faster than the bottom surface. This is the bottommost surface. This is bottom surface. Bottom surface. This is the top surface. Is faster, dissipate faster. Because of the faster, it will try to get contact. However, in the bottom surface will not uh, give the restraint to this contraction. Okay, so there is a change in stress. Because of change in stress, the the crack will appear, and the bottom surface become this still remains one mark. So they appear. So the first statement is the mass concrete due to the creep. There is possibility of decrease in cracking. However, it is possibility of enhancement in cracking. It enhance the cracking possibility. Okay, in tall building, now the second question is, the second statement is that in tall building, differential creep in outer and inner column may result in additional movement. Okay, so so what happened, this yes, actually the tall building, what happened, this is the column, this is the columns are there, this is the columns, the columns, the columns. So this is the outer column. See, if you consider this the outer column, this is the inner column. This outer column, outer column. And these are the inner column. Now here the slab is there. Slab is there. Okay. Now there is a 3D. If you consider, now the load is coming here. So this the load is coming here. If we if we observe, then this outer column, because of uh, this edge, it the effective area it comes is this much. However, inner column it is around two times. Okay, so so actually this outer column, inner column shares more load. Inner column shares more load than the outer column, and it is okay. So internal column shares more load, and outer column share half of the load as shared by internal column, and this is half, almost is approximately half of this load. Okay, so if you consider this load, uniformly distributed load, and so it is half of this load. So outer column shares lesser dissipate or transfer the lesser load than the inner column. So due to this difference, the differential creep in inner and outer column may result in additional movement. So because of this this difference in stress condition, it will movement. The outer column will be, there be some deformation. The deformation of the outer column is much due to the creep will be lower than the inner column. So there will be differential settlement, such type of thing. There, in a overall, you can understand in layman language. You can understand. So this is additional movement. Now creep result. So the second statement is true. So I think the first statement is false, right? There is possibility of creep decreasing is cracking. Okay, enhancement of cracking. That's already mentioned. So now statement 3 is the creep result in loss of prestress in prestressing structure. Yes, loss of prestress because of the relaxation. Yes, loss of prestress because of relaxation, and creep also results this loss of prestress. And because when the creep is happening, so I've already show you this 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 pre-stressed. See, this is a pre-stressed concrete. Now, because of this creep, I think So because of this creep, uh, because of this creep, this loss of pre-stress can also happen. Loss of pre-stress also can happen because of the relaxation. Okay, because of the relaxation or yes, the creep means this pre-stress loss means this um, because of sustained loading, because of this sustained loading, it will try to deform mode. However, because of the stress, this may not deform that much. So there will be some difference in deformation due to creep and also the stress condition, considering these two phenomena. So actually this ultimately results to it affects the pre-stressing process. So this way you can understand this statement. So 2 or 3 are correct. So now the sixth option is there. Now this sixth. So I think it is the statement 2 and 3 are correct. Last six. The sixth problem is drying shrinkage is completely reversible. Okay. And this drying shrinkage, uh, drying shrinkage is completely reversible, and this after drying, if we pour water, if we add water again, the water will be absorbed and shrinkage will be reversed. So this statement, the assertion is not correct. The assertion, this statement, assertion statement mentioning the assertion is not correct, because the drying shrinkage is not completely reversible, partially reversible. So this thing, if you say, uh, yes, the shrinkage is not fully reversible because of this formation of additional bonds. Okay, not fully reversible. Yes, actually, talking about the drying shrinkage. So drying shrinkage, there's a small graphs are there. So this is the graphs, and this is the deformation. This is deformation or creep, whatever. This is deformation. This axis, this age is this axis. Now I consider this is one is there, and another is there. So actually, it is whenever the concrete stored in water, it is stored in water. The creep will be much less. But in what condition the creep can't have? The creep it will decrease the creep, or it decrease the tendency of the creep to get happen. And it is the stored in air. It's a dry condition. If you consider it stored in water, consider it as dry, stored in air, stored in air. So what happened with the age? If at a certain time it will yes, the string at a certain time it will after deformation, the deformation will come, means the shrinkage, the deformation will be increasing. It will be increasing due to creep. and then it get reduced. It gets reduced, and if upon certain addition of water, it can also be reversed. So this is the reversible shrinkage. This is the reversible shrinkage. Reversible shrinkage, and it's the irreversible shrinkage. Irreversible shrinkage. Irreversible shrinkage. 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 Now, if we consider about reversible drying shrinkage, if we make a continuous graph, so what does it look like? What does it look like? This is the storing water, and this is the ultimate shrinkage. Beyond this shrinkage is not possible. So this is the shrinkage plot or deformation plot. Whenever there is a water so deformation, um, with age, with more water, if it is stored in water, then obviously the shrinkage will be less. So, however, still there will be shrinkage. Okay, and it's certain age at a T naught. We are giving some load. We are sustained load. Okay, a sustained load, and the deformation will take place. It take place and it will deform. Okay, and it will deform, and then after deformation, air is there, and the shrinkage will come. The shrinkage will come. Is it, and then we are weighting it. This is the shrinkage. So this plot is the shrinkage plot. If I say the shrinkage deformation or volume change, is getting occurred, and with the addition of water, it get down. Okay, and then when get water get evaporated or out, it again shrink. Then it is waiting. It is waiting. Then it is drying. So repeated waiting and drying, repeated waiting and drying, repeated waiting and drying. So this way it happens. However, this is reversible shrinkage. This is reversible shrinkage. Reversible shrinkage. So this shrinkages can be reversed or can be recovered. Okay. So the fourth question, the drying shrinkage is completely because air in we are kept in air, so it is dry condition. So here the shrinkage is much more, and if we wet it, then it will come down. And when the water get removed, it will get shrinkage will move, getting higher, and then it will add the water. Then the shrinkage will burn down, and this is in this way it continues. So this is not a completely reversible. So after drying, if we add more water, the water will get absorbed, the shrinkage will be reversed. So actually the both assertion and uh, reason um, are see this part is not true. This assertion is not true. However, the reason they say that this is also a statement, is a correct statement, but it is not a correct explanation actually. In some way it will get reversed, but it is not getting fully reversed. Okay, so the reason is also true. Okay, however, it is not fully true. Okay, so this way you can understand. This is not a correct explanation. Obviously, it is not a correct explanation. But the reason is not the statement is true somewhat. In some to some extent, it is correct. However, there's flaws also in the statement. So now the seventh point is the You take your attendance. Now the seventh question is the this I think this the assertion is not correct, not correct, and the reason is correct is correct to some extent. It's correct to some extent. To some extent. Now the which of the following increases the with increase in volume to surface area ratio. You know, when the volume to surface area ratio increases. So volume to surface area I've already mentioned. If it increase, the which factor increase? Creep shrinkage or both the creep shrinkage or neither of it. Okay. So actually when the yes. Mm. When this volume to surface area increase means surface area is less. Surface area is less. So less surface area gives the less evaporation. Less surface area is less evaporation. Okay. So so less evaporation. So less evaporation means and less water will be moving from one gel pore to another gel pore. So it leads to the less creep. Creep will be less. That is understandable or that is clear. And now if I consider the shrinkage part, okay. Now if you consider shrinkage, yes. Now we consider the shrinkage, the graphs are there. They consider the if you consider shrinkage, when the shrink how it the shrinkage comes picture, the shrinkage is there and this shrinkage is what is there. Okay. So shrinkage by yes, shrinkage is there and yeah. So there's a two plot is there. One is this plot and one is this plot. This plot is the sandstone aggregate. The sandstone aggregate. This is the gravel aggregate. Now this is the ultimate shrinkage. The shrinkage is in there, and this is the this is the V by S. Here is V. So whenever the yes, this is see this is the volume. This is the volume. This is the surface area. Okay. So more volume means see if we increase the volume surface area this is the surface area. Yes, this is the surface area. Okay. Um, so yes, the actually the volume to surface area. This volume to surface area, if we say volume to this ratio of volume to surface area, if you say if you are increasing it, so surface area is lower. So if the surface area is lower, then the volume to surface area ratio will be higher. So for higher volume to surface area, so shrinkage will be lower. What happened because of the less evaporation? See, the surface area is less. Surface area is less because of the less surface area. There will be less evaporation, and because of the less evaporation, the shrinkage will be less. So I already told you the shrinkage is due to the moving out of water from the from the gel ports, or we got water from the gel ports. Okay, it's emptying the capillary water or emptying the gel water, gel system. So this way you can understand. So shrinkage will be less. So so it is for neither creep nor the shrinkage is affected. So 7 is the neither the creep, neither of creep, neither of creep nor shrinkage. Nor shrinkage. Now, as evaporation happens, more water moves from ports to what type of ports to another other ports. So that is the thing. So I'll come to this. The point is, and the ports actually when there is shrinkage. Shrinkage occurs due to the evaporation pressure is much more than the capillary tube, that is capillary pores. It is filled with water. It will get dried out. The water will get removed from the capillary pores, and with the and due to then this drying, the volume change will occur. So if and also this and also this here the surface tension also takes place. The lesser the radius of the capillary size, more the surface tension, and pores gradually become empty according to the size of the capillary. So and actually it starts from larger hole to smaller holes. One by one, it get empty. Okay, and larger holes. I think larger so the larger dia holes means that larger dia capillary. The surface tension is much less than the smaller dia capillary, because in the smaller tube you can check in the smaller the tube capillary, the surface tension is much more, considering the meniscus. So larger pores first get emptied, then smaller pores. So thing is this evaporation, when there is evaporation, first this larger hole get emptied and then the smaller hole. So it another way it can be said that water moves from larger to smaller holes and larger to smaller holes. Now, ninth question is that now these factors affecting the shrinkage. So, but these things are the modulus of elasticity. Modulus of elasticity of the aggregate is there. So this is for the elastic modulus of aggregate. So consider the E aggregate. E aggregate would say. So this aggregate system, this aggregate is there. This aggregate is there, and with the paste system, this is the paste. This is the aggregate, and this is the paste. Okay, and whenever there is the load is coming, so previously, say this is the surface, or this is the surface, and the concrete paste is there, and this is a particular. I'm just exaggerated the view. The load and a load is there, because of the load, there will be shrinkage. Will be shrinkage or volume change in in paste, because the modulus of elasticity of the paste is much lower than the aggregate. However, at the same time, the aggregate will not let the paste to shrink. So there will be a reverse action. So there will be a reverse action, and it will be upward from the aggregate side. Okay, for same stress level. Okay, so higher the E aggregate, this higher the modulus of elasticity, shrinkage will be less. So the decrease in aggregate modulus, so it is in reverse. It can be said if it is E of aggregate, if it is reduced, then the shrinkage will be more. So first statement is correct. Now the second one is the increase in volume of the aggregate. So volume of the aggregate means, and the actually volume, if the paste content is much more, it shrinks more, and if the volume of the aggregate is more, it shrinks less. So cumulatively, or as a result, overall, increase in volume decrease the shrinkage. Overall, increase in volume of aggregate decrease the shrinkage. So actually, this is also a plot is there. This plot also plot is there. This is the relative shrinkage. This is the shrinkage, relative shrinkage, and this is the volume of the aggregate. Aggregate. So it's a curve is like that. Okay, so more the volume, less the less is the shrinkage. So the second statement is also true. The increase in volume of the aggregate, decrease in shrinkage. Okay. So increase in curing period. So increase if you increase the curing period. So curing, if you increase the curing period, then more hydration will take place, and there'll be more bonding, and there'll be no differential or other factors would involved or in developing the strength. The concrete will achieve the good strength, and the shrinkage will be less. So increase in curing period, shrinkage will be less. Okay, so actually we are giving the more water due to exposing the concrete to the water for a longer period of time. So shrinkage will decrease. Whenever the loss of water is happening, the shrinkage will come in picture. So because of if you increase the curing period, then at the same time we are giving exposure to the concrete surface more to the water, then it ultimately decreases shrinkage. So this third statement is correct. However, decrease in relative humidity, it shows the decrease in shrinkage. So actually relative humidity, there is a I think this graph is there. So this is the plot. This is relative. This is the time, and this is the shrinkage strength. Alright, okay, shrinkage is there, and this is this, and this is the for 50%, 50% relative humidity means saturation, whatever it's 50%. Is 50%, is 70%, this is 100%. Now, more the relative humidity, lesser the shrinkage. So Actually, and this thing says yes. Now, if I say that yes, so so dryness. Actually, now if you consider this thing, dryness occur when the evaporation due to the evaporation. So the capillary water will get out by the evaporation, and capillary becomes it tends to dry, and interlayer water will move out from gel pores to the capillary pores, and movement of water capillary pores and movement of water from the gel pores resulting shrinkage. Okay, so whenever the relative humidity is much more, shrinkage will be less. Shrinkage will be less. So I think this this fourth is also true. Fourth is also true. Okay. So the first one and two is okay, right? And this more higher the E modulus, shrinkage will be less. Higher the higher the aggregate modulus of elasticity of aggregate, lower the shrinkage. Lower the shrinkage. So in reverse, you can say lower the aggregate modulus of elasticity is higher the shrinkage. Is correct. Second option is the increase in volume of aggregate. Volume of aggregate. If we increase the volume of aggregate, more volume of aggregate means less shrinkage, decreases shrinkage. Now, if I not consider this third option, is fourth, the decrease in relative humidity. Decrease in relative humidity increase the shrinkage. Actually, yes, it's correct. Decrease in relative humidity means this is drying. Decrease in relative humidity means it's getting dry. And this is getting dry. Getting dry means more interlayer water will move out from gel pores to the capillary pores. Okay, so whenever there is movement from the gel pores, if the water kept reside in the gel pores, then the chances of the this shrinkage will get reduced. However, if it moves from gel pores, it is leaving the gel system and it is entering the capillary pores, and from the capillary pores it will get evaporated, or due to the evaporation pressure or other pressure it will get evaporated. So if that happens, then there will be shrinkage. Ultimately it results in shrinkage. Okay, so whenever the relative humidity is less, the shrinkage will be more. So so I think this relevant actually 1, 2, 3 is correct. Now 10. Now this 10 question is saying, and which of the what are the effects? What are the effects of the shrinkage? What are the effects of the shrinkage? This yes. This is actually the shrinkage quantity magnitude is measured by the ring test. Okay, and you also heard about it where the concrete is filled in a annular section, and in annular inside the section there is a strain gauges, and there will be some other factors also come in picture where the expansion or shrinkage, the shrinkage in concrete get identified with the strain gauges that are attached inside the inner circle of the annular section. Okay, so and dry and autogenous shrinkage also measured by the ring test. And this effect of the shrinkage is one said can be said that loss of pre-stress is effect uh, restraining. If there is increase in cracking thin section. Okay, effect of due to of the restraint shrinkage. This is the restraint shrinkage cause cracking in thin section. Okay. And other effect is loss of precision, additional movement on tall bending. In tall bending, differential shrinkage of inner and outer column results in additional movement. So I think already I mentioned this three part, because this now if I say this is the thin section, so this is the concrete block. This is a concrete block, and this is thin section means this is 200 mm thick. 200 mm thick. This is thing is called the thin section. Now, if this shrinkage would happen, it will the crack will be throughout the section. The crack will be throughout the section, and also there will be loss of pre-stress because of this shrinkage. Because the stress is getting the stress concentration is getting removed. Okay, stress concentration getting removed, and additional movement of tall building also takes place, and additional movement because of this shrinkage in shrinkage of inner and outer column is difference in shrinkage in inner and outer column because of the differential area or the difference in deformation. This additional movement will come picture. So I think the statement 1, 2, 3 is correct. So 1, 2, 3 are correct. So with this, I think we covered all the questions that are mentioned in today's assignments. However, there's a few points are also there that will be quickly. I am going through the points. The first is the this what is the this this is autogenous shrinkage. Autogenous shrinkage occurs in a sealed specimen because of the creation of the empty spaces from water filled space by hydration, and uh, and if it is self desiccation is there. Self desiccation means the evaporation of water or dying out of water. Okay. Yes, if the specimen is sealed, now I made a concrete block and I seal the specimen. Seal the specimen afterwards, after formation of the concrete get formed. When the hydration takes place, actually, if you check after the hydration, there'll be volume change. There'll be some volume change after the hydration product. Whenever there is hydration product, there will be some volume change in that. So, however, because of the restraining mechanism, if I put the restraining, so there will be volume change of the material from previous state. So it will not get it will not be able to change, or it will not get achieve. It will not achieve the desired shape after the hydration process. Because of these differences, the shrinkage will come in picture. And how it is happened? Because the seal specimen, a creation of the empty spaces from water filled spaces. Water fields. Yes, because of the creation of the empty spaces from water filled space by the hydration. Actually, what happened because of this hydration process, this one previously what the actually the hydration products consumes a less volume. So previously it was more volume, now it is a lesser volume, and previously it was occupied by the water, now it is not, and it is get empty spaces. Okay. Is empty space is getting created. So due to this autogenous shrinkage can occur. So this way autogenous shrinkage can be defined. Now, if I quickly go through this all the key points today. So now I'll be discussing few points that the key points today. So creep is the tendency of the solid material to move slowly or deform permanently under the influence of the stress. So creep occurs due to the long-term exposure to a constant stress level that are below the strength. So it will not fail. So it will not fail. However, the constant, if some other factors involved, it may fail. Only Okay, so this is a constant stress. The two things are there. There is a constant stress that below the strength. or FCK or something, and the constant stress and long term, long term. Okay, so creep visible in metals, polymer, concrete, and creep of the concrete is quite different also. So if I plot the graph, then it looks like mostly this way. So see, this is the constant level of stress. Now at the T equal to T naught, we are applying the stress, and we maintain the stress sigma naught for a long duration of time. This is constant stress, constant stress. So this is the loading curve. Now if I consider this deformation, the strain is there. Now the strain is there, and the age is also there. And at a T naught, at T equal to T naught, at T equal to T naught, there will be instantaneous elastic strain. Instantaneous elastic strain means initial elastic strain means you have a removal of the stress, the recovery can be possible. So the deformation will be get recovered. So this is the instantaneous stress, and this is epsilon naught. Epsilon naught, okay. And after this elastic, this is the initial initial elastic strain. Elastic strain. So it is nothing but sigma naught by E. Now afterwards, if I keep on maintaining the load, it will be the non-linearity will come. Non-linearity will come, and there will be creep. So whenever the creep get happen, it will irreversible. So this is the creep. This is the creep after the after T equal to time T. So this is the creep. So it is. So this is this strain curve. This is the ET. So ET, then creep is nothing but ET minus E naught. Sorry. So ET minus. So ET minus E naught. So this is the creep. Now, if I so this is the one point, and another point is if I keep on increasing, because and here this also maintain. And now I want to show you another part. Now if I consider the stress strain behavior, this is the stress, this is the strain, this is the strain. Okay. Now this is a stress strain curve for this is a stress strain curve for 7 days. This is a curve for 28 days. This is the uh, okay. So stress strain curve after 3 days or 7 days or 28 days, 20 days, 3 days, 28 days. Okay. So this is the stress strain curve, and here the sigma naught is there. The sigma naught is there, and correspondingly strain I'm also getting for 7 days. And if we see that for a particular stress level, if we keep on maintaining stress level, that deformation is getting increased. For 28 days, for 28 days, creep is much more, but 27 days, the creep is less. Okay. So, and ultimately, 28 days, if you say epsilon naught here, epsilon T here, so creep is epsilon T minus epsilon naught. So this is the and this is the modulus. With this with the days, the modulus of elasticity also getting changed. Also getting changed. For a same strain level, we are getting different stresses. So modulus of elasticity also getting changed. Then we have also discussed this creep relaxation. Okay, so creep relaxation, I think it is easy. Now it is easy for you to understand. Now it is this is creep recovery. Okay, so after the relaxation, what happened? So now the relaxation. See, this is this. um, this is the constant stress. Now, if the relaxation means this, we are giving restraining mechanism. With the restraining mechanism, the tension will come. So previously it was compression in the pre-stress. Now the tension is coming. Now it is getting neutralized. So what happened? Instead of this curvature, it will get a downward connect, downward. Uh, instead of this. So at T equal T naught, this is the stress, this is the stress, this is the age. It's the age is there. This is the sigma naught. We are reaching to the sigma naught. However, because of this relaxation, it is come down to sigma t. Sigma t will come down to sigma t. Sigma 2. So relaxation will be sigma naught minus sigma t. Okay, with the age. Now creep and relaxations are also varies with the time. That's also and in the resistance specimen creep get reduced. Is obvious is get reduced. Now creep recovery. So creep recovery is withdraw stress. Um, yes. When see this is the this situation is leads to the creep. However, when the if we want to some amount of creep recovery, we certain point of time we are removing the stress. Still, if we still remove the stress, there will be still some permanent deformation. This some already creep already happens, so it will already deform the section. Still, there will be some deformation. So the curve this is the relaxation. This is the relaxation. This now it is creep recovery. If you check this creep recovery, then this is the sigma naught. This is the age. Now this is the strain. This okay. So this is stress level. Now after this is the wet condition, stored in wet condition, and it is stored in dry condition. Okay. If I the stress getting removed after this age, that is some certainty of time, so it will reduce. It will reduce. However, there is instantaneous recovery. So, so if you consider is the strain, this strain is the recovery is instantaneous recovery is the this instantaneous instant instant recovery. Yeah, instantaneous recovery. Instantaneous recovery, and now it is the this is instantaneous recovery and it is the quick recovery. When the curvature started, it's a quick recovery. Gradual recovery also obviously gradual recovery. Okay. Now this is so and it's dry condition. So dry condition, I also told you the dry condition creep is much more than wet condition. So in wet condition, similar thing is happen. So similar thing happen. So there will be also interesting recovery. Also the creep recovery is there. So this creep mechanism is still unclear and generally related to the absorbed or interlayer water and the concrete after removal of evaporable water exhibit little creep. Concrete creep occurs at all stress level within the surface stress and linearly dependent on the stress when the pore water is constant. Now drying creep occurs when the water moves out. Water moves out when it moves out and internal movement of water to the empty pores in the cell specimen causes the creep. Okay. So when there's the movement from one pore to another pore, there's the pore with full of water, there's gel pore, there's water is there, another gel pore, the water is no. So there's the pressure differential is there, and due to pressure differential, the water will get moved into the just pore. So in the sealed specimen, obviously, so the creep will originate. The creep originate in CSA gel in hardened Portland cement, obviously. And in case of dried, when water is removed, the creep is caused by slips due to bond rupture along the bond restoration at the adjacent site. Continuous hydration process or aging and large surface of gel have roles in the creep. Okay, the concrete experience the gradual change in response to the stress environment and thus extremely complex thermomechanical behavior includes the creep because whenever the thermomechanical behavior comes in picture, it also influence the creep. So factors I already mentioned to the elastic modulus, water cement ratio, curing conditions are there. Okay, conditions are there. So and each and everything I already showed in with the graph. So I think there is no need to repeat further. So predicting the creep, there's the various type of formula is there. Formula is there where the creep at certain time t c t c t is there. For saturated concrete, is the c at 28 days creep. What is the 28 days creep? And 5 t to the power 0.2 for saturated, for saturated concrete. And CT equal to C28 minus 6.19 plus 2.15 LNT by 1 by 64 for drying concrete. Okay, tree increases with the tree increases, this creep reduces because of the ln factor. Now methods appropriate. Okay, the normal weight concrete under the constant environmental condition is estimated for the creep. Normal weight concrete mentioned in the ACI. So creep mentioned is the measurement of the creep is mentioned in the ACI method, ACI 209 R. 209 R. The specific creep at any time T. Uh, that is C. The specific creep at any time T naught is the creep due to unit stress applied at T naught. So it is the creep when the stress is the 1 unit. So creep coefficient is T naught is the ratio of the specific creep to the initial elastic strain. So creep T naught is not this creep at the T at time and with the initial elastic strain is the ratio of the creep at time T with the elastic strain. Now the ultimate creep coefficient is T infinite T naught is the long-term creep coefficient and can be related to the creep coefficient at any time. So how it get related? So it actually the ultimate creep coefficient is nothing but t creep coefficient at t equal to t. So whenever the t is infinite, this ultimate creep coefficient is obtained. So it is nothing but t minus t naught into 0.6. So 10 plus t minus t naught to the power 6 at t in infinite t naught. Okay. So these are the few factors. So and actually this CT creep at time t is a function of the creep coefficient at t, and it also comes. You can just multiply it. This okay. So now this t ultimate T naught is the factor related to 2.35 K1, K2, K3, K4, K5, K6. So these are the factors. These factors also have the formula. This K1, the K1 is the curing. It depends on the curing. This K1 depends on the curing. And there's also a formula for 7 days and 3 days. That formulas there to calculate this K. And this is the curing condition. Depends on the curing condition. K2 depends on the relative humidity. Relative humidity is related to relative humidity, and is also the formula is also there for relative humidity more than 40%. K3 is the depends on K3 depends on this volume to fraction ratio. I think you can have already keynotes or the notes based on the Professor Bhattacharya lecture, and there's also tabular form table is there which mentions this V by S versus K3 value. So but you can also check more the if you increase there's a more the value of the V by S. More the value of V by S means lesser the surface area, the creep coefficient will be lesser the surface area means less evaporation will take place. Lesser the surface area means less evaporation will take place. so creep will be less. That's why this K efficient with the increase in this V by S ratio, the K3 will also get reduced. Okay, so when K4 is the K4 also depends on the slump. Okay, so more the slump, more the creep coefficient. Okay, slump means the deviation from, if you already go through this slump process, so plasticity is much more, then flowability is there, then the creep will be much more. So higher water content also gives the higher slump and also results more creep. And K5 is related to the fine aggregate to total aggregate ratio. The fine aggregate AF by A, fine aggregate to total aggregate ratio, and its formula is that to 0.0024 AF by A. Okay, so the case is related to air content, which is nothing but 0.46, 0.098. Okay, A is the air content. Okay, and there is also the creep coefficient for the elastic strain. The creep coefficient is the function of the the creep coefficient is the function of the elastic strain, and the creep deformation. Creep deformation at unit stress, under unit stress. Okay, so there are formulae are there, and this is nothing but creep deformation is 1 by E T naught. Okay, at and T naught with initial elastic strain, this linear portion of the curve, the E of the linear portion curve, and this C creep at T equal to T naught at any time T. So it's nothing. If you check it, if you E by T naught, I think this is already mentioned by Professor Bhattacharya. Still, I'm doing these things. So this is this, so you can calculate this phi. So E is related to the cylinder strength, F cylinder, or the cylinder strength derived from the experiment. Okay, now. And now that's also the creep and sink in the lecture 8. Um, you can also obtain this E T naught with the E28 is 28 days elastic modulus with E28 0.4 plus 0.6 by FCU T naught by FCU 28 days. So these things are the strength ratio. This is the strength ratio. This is the strength ratio. Strength ratio is there. Okay, so the strength ratio is the 0.7 for 7 days, 1.17 for 90 days, 1.25 for 1 year. And also there's also E28 also happens this 20 plus 0.2 FCU ultimate strength 28 days. So these things are there, and measurement of the creep also done with the ASTM measurement. If you keep creep measurement also done with the ASTM code C512. Okay, so already mentioned that we have already mentioned that how this nut is connected and how the concrete cylinder is get compressed with the piston. Okay, with the nuts. So already we have discussed this thing at the beginning of the class. We're discussing the assignment problem. Now the effect of creep, the increased deflection in flexural member. Yes, it is this is the member is there, and this is the UDL is there something, and with the elastic deformation it comes to this. However, when the creep comes, so it will deform more. So this is the creep deformation. This is the creep. So E must account this creep. So whenever you are designing this E value, so during the serviceable life of the structure, so E should be such that this creep, if you creep is can be avoided, it can be prevented in any cost. So if you have already this stress versus strain curve for different days, for something see 7 days, 28 days. So the creep will be getting more with age. So this has to be taken in consideration while designing. So creep results in gradual transfer of loads from concrete to rebars in the column, and when the steel yields further load, it transfers to concrete. Actually, this concrete column is there, and here the load is transferred to the rebars are there. When and this concrete transfer the load to the rebars, and when the steel get total load, full amount of strength of the steel is get utilized, it also transfer the load to the concrete below of it. So in eccentric columns keeps increases, because in eccentric columns, whenever there is a columns is there and is a central line, there will be some point load here, so this is eccentricity, the moment, because and along with this axial, along with this axial load, this moment also come in picture. So because of this load, change in the load pattern or moment, which is the additional moment, and also the point load, because of the eccentricity, creep also get increased. So with the sustained loading, actually the sustained loading gets cumulated because of this moment also get higher. So now this the statical indeterminates we already mentioned, and for the mass concrete, how the temperature is affecting. Okay, so we have already mentioned in the beginning of the class how this outer periphery columns share the more load than the inner periphery column, and we also discussed about this fatigue and secondary creep. Actually, fatigue is nothing but the number of cycles of reversible stresses. Actually, we can also say that creep is a fatigue thing, because if the cycle is long, it's not a infinite, for an infinite cycle, infinite for infinite age or duration, and the cycle means maintained. One cycle is so tension is there, and then compression is there. Then we can also say it is not a, it is creep. The creep is not a fatigue actually. Fatigue is actually is the if the cycle is frequent, the frequency of the cycle is much higher, then the reversal stress is come. So these things you have to be keep in mind. Okay, so actually the concrete exhibit 60 to 70% of the strength if the load is applied. This there is a primary creep, secondary creep, and tertiary creep stage also there. Okay, so already we did it in the graphical way. Okay, graphical way. Secondary creep, in secondary creep, creep rate is high. The number of cycles to failure is low. Okay, the secondary creep, the figure is there. And also this minus rule is also there. Through minus rule, we can identify the number of cycles. Number of cycles is subject to the failure. Okay, so now here the fatigue comes in picture. Actually, in the certain creep, it is not happen. However, if I change the cycle from one regime to another regime, if you change the stress regime to, and it is you subject it to the particular one structure, how the structure, in what at what cycle it get failed. So we get it through the minus rule. So minus rule is nothing but this n1 by n1 plus n2 by n2, n3 by n3, like that, nk by nk equal to 1. Okay, so n is the capital N is the number of cycles to the failure at a certain stress level. This is the number of cycles to failure at certain stress level, stress level stress level. And now the n1, small n1 is the small n1 number of cycles subjected. This is number of cycles subjected. Okay, so with this two, if this two ratio is equal to one stress regime, and this another two, another stress regime, cycle two, cycle one, right? That, so if the two cycles are subjected to a particular structure, then these two are coming picture. These two things are known, these three things are known, and it can be asked with this quantity. What is the quantity? So you simply equate, make it sum of it and equate to 1, and we'll easily get to the N2. So this way you can apply the minus rule. So now the creep is the movement of the water in gel pools already mentioned. Now shrinkage is also part of the creep. Also is similar to the creep. The creep also shrinkage also movement of water in gel system, movement of water out from the gel system actually. And sink in this in concrete, shrinkage occurs due to hydration process. As volume of hydration product is lower than the original volume, loss of loss of volume takes place. With loss of volume, it shrinks. Okay, so volume strain is the okay. So um, drying stage, drying sink is also there. So there are lots of sinkage type. The volume strain is the 3 times to the linear strain, and we generally measure linear strain in micro uh, micro strain level. So volume of the hydration product is smaller than the original volume on unhydrated product. Unhydrated product of the cemented water, this paste is 0.06 CH, and reduction is volume resulting in chemical shrinkage. Autogenous shrinkage, I already mentioned, this is the microscopic reduction in length under constant temperature without any moisture migration to or from the concrete. So autogenous shrinkage is still concrete. Okay, so still concrete, the hydration already take there. There will be no incoming or outgoing water is happen taking place. So whatever the shrinkage is there is the autogenous shrinkage. Plastic shrinkage is the volume change that the concrete undergoes during the plastic stage due to loss of water by the evaporation. Drying shrinkage occur in the hardened concrete. It can be occur in 1 to 2 months or in 6 months. Results crack, and this drying shrinkage results crack in thin section. Okay. Mm, and now this evaporation, how the for the philosophy of how the cracks occurs. This is the concrete blocks. Now on the top of the surface, this evaporation takes place. Evaporation starts. This is the evaporation. More water which is below here, so it will be moved move to the top, and it's just by the law of third law, it will just drag the solid from top to downside. So solid gets separated out, solid get settled down. So because of solid gets settled down, the volume get reduced. If the volume gets reduced, the change in volume, so cracks will occur. So this way you can identify this shrinkage. Now, there is also drying shrinkage. How the reversible drying shrinkage I've already shown you with plots, and there's also carbonation. So carbonation shrinkage means when the carbon dioxide at the atmosphere, from atmosphere, carbon dioxide reacts with the calcium hydroxide. It generates the calcium carbonate and H2O. This calcium carbonate is CO2 from atmosphere. CaOH voltage is acts to this, and it reacts to CaCO3 and H2O. Okay, so CaCO3 volume is less as compared to CaOH voltage. This calcium hydroxide, so volume get reduced and shrinkage occurs. So now the shrinkage, uh, the lecture 29, the shrinkage. Uh, there is no robust theory related to shrinkage. Shrinkage related to the absorbed interlayer gel water. The movement of interlayer water out of the gel results in reduction in the volume of CSH. Capillary tension is set up by increasing the curvature of meniscus. More the curvature, the more the capillary tension. Okay. So at lower humidity, change in surface energy of the CSH due to removal of the firmly held water molecule is thought to be the responsible for reduction in the volume. Okay, so so this is how you can identify. Now, thus the shrinkage is not a fully reversible. So fully not reversible, drying shrinkage is more prominent than other shrinkages than normal concrete. Autogenous shrinkage I already mentioned. With low water cement ratio, autogenous shrinkage may be more than the drying shrinkage. Okay, so with more elastic modulus of aggregate, the shrinkage will be less. With more volume of the aggregate, the shrinkage will be less. And okay, so these are the things, few things that you can count. Yes. So now there's also the relative humidity. more the relative humidity is the shrinkage. Already mentioned how this relative humidity affects the shrinkage. Also, there is a volume to surface area effect on the shrinkage. How it is getting affected the ultimate shrinkage. Okay, so also the prediction of the drying shrinkage is also there. The formula is also there where similar to the creep also the here this K1, K2, K3 in up to K7 factors there. So K1 is the steam curing. It depends on the this is ultimate. So S not ultimate shrinkage at ultimate shrinkage. The difference is 780 between the 1 minus 6 K1, K2, K3, K4, K5, K6, K7. K1 is the steam curing. This is depends on the curing. This K2 depends on the humidity as RH depends on the RH. K3 depends on the volume to surface area ratio. K4 depends on the slump. K5 is fine aggregate to total aggregate ratio. K6 related to the cement content. More cement content, the more is the cement content. When the cement paste is more, the shrinkage will be more. Okay. Finally, the K7 is the air content. Air content is there. So so there are also some British methods are also available. We for measurement of the shrinkage pressure on the concave and okay. So there are the lots of methods that available in the after the British standard where the scripts shrinkage at T equal to T naught can be measured. Okay. So there's formulas there is 28 100 3.61 ln T minus T naught 12.05 into half. These are the formulas, and now shrinkage will come. How this shrinkage takes place? Okay, so there's also the evaporation, pore pressure also there. So actually, and this is the cylinder. This water is there. Water is there, and when you are putting some pressure, then some part of the water will get evaporated due to this due to this phase changes. Okay, the molecule get squeezed out and comes out. So it is get vaporized. Okay, so escapes as gas. So like grief shrinkage is also less understandable. Psychological chemical psychochemical fundamentals also improve the understanding. At a liquid gas interface, when the pressure is applied on the liquid, vapor pressure increases, molecules are squeezed out from the phase and escapes as gas. So there's a lots of equilibrium equation where the mu L, this is the chemical energy, chemical potential of liquid equal to chemical of the gas. When this happens, this evaporation takes place. Okay, so liquids tend to adapt the shape that minimizes. Always liquid try to minimize the surface area and to have the maximum number of molecule are interacting with the neighboring. Have maximum number of molecule interacting with the neighboring ones. So work done. There's also work done is there. So work done to minimize the area. So gamma dA. The gamma is the nothing but the surface energy with the energy per unit area. There's a surface tension forces. Okay, so these things are there. There is also this inner if the inner pressure from there is a fluid flowing from the tube section. So inner pressure is much more. Inner pressure is much more than outer pressure. Outer surface pressure on the concave side. So on the concave side, the inner side of the curved surface is always higher than outside. There's the convex side. So this P in equal to P out plus gamma 1 by R1 plus 1 by R2. This R1 and R2 nothing but this curvature. These two curvatures. Whenever this sheet is there, this is the concrete block and it is thickness and there this is surface tension force are creating and the curvature is taking place. This is the curvature taking place. This 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 is R1 and R2. This two curvature. So with two curvature, these things are coming picture. Where there is additional when there is a spherical. So R1 R2 equal to R. So P out plus 2 comma by R. This is the surface tension forces. Uh, okay, so surface tension forces 2 comma by R. So inside the excess pressure, this 2 gamma by R changes into the vapor pressure. Okay, since the curing of the surface gives rise to a pressure differential. Actually, when you're curing to the surface, there will be the pressure differential from outside to inside. So a pressure differential of 2 gamma by R. This will come. This will come in effect. So and there's also some empirical formula with the pressure, vapor pressure P equal to P naught equal to E to the power gamma by R Vm L by RT. So Vm is nothing but this nothing but this Morse volume, and R is the small r is the smaller the radius of the capillary. More the lesser the radius of the capillary, more is the surface tension forces. Okay, so and R is nothing but this gas constant is the temperature. Okay, at R equal to infinite, P equal to P naught at the flat surface, no evaporation takes place. So at R equal to infinite, P equal to P naught. Okay, vapor pressure. Yeah, vapor pressure is equal to the ordinal vapor pressure before uh, the before the curvature So it is a flat surface, no evaporation takes place. So pores gradually become emptied according to their size. So larger and softer pores, smaller pores I already mentioned. So and there's also things is the water has tendency to spread and increase the perimeter, and comes under tension. So you see, this is the capillary tube, and here the this water is there. Water will come from bottom, it will be inside. So here surface tension will act. So however, at the bottom there is no surface tension actually. However, in the top, because of meniscus, the surface tension will create. So induces compression in the solid. Actually, when the surface tension is there, actually from the this force and this particle, this is this is the this capillary this is the capillary. So this is because of surface tension force, there is the surface tension, it will drag down, it will drag these particles, these particles will be the compression will be there. Okay, so compression will be on the space skeleton. This is small particle. Here the small particle is there, and between the pores are there. Here the capillary rise will take place, and it will ultimately give the compression to the paste particle, and in such way the paste will get compressed. So the cracks will generate. Now this Okay, so the when the absorbed water is coming picture, so this concrete surface is there, and inside in the this molecule is it's distributed. It's the same pressure is subjected to this molecule. However, at the surface, the molecule is subjected to this downward pressure. However, this absorbed pressure neutralizes this effect. Okay, so molecule well below the surface is equally attracted by all the surrounding molecules. And however, actually, I'm talking about these particles, concrete particle, and also is applicable for the fluids. However, if molecules near the surface only have the downward force. Now the molecule is what the molecule is absorbed, particle absorbed, it reduces the downward force, and this also happens in CSHL. Okay, so these are the few points you can mention. The measurement of shrinkage is done by the IS 9459. Okay, so chemical shrinkage is also measured by this is measurement of the chemical shrinkage. Leach atelier method also method is used for the cement paste. Uh, we're keeping in the rubber bag, uh, or volume change is measured, and shrinkage is get measured. Chemical shrinkage is measured by the ASTM C160817. Okay, so these are the thing for points you can note. Okay, I think I have discussed most of the points. Sorry, I have not been able to discuss those MCQ questions. We'll be doing in next class. Thank you guys for attending. Thank you. Good night.
Thank you, sir. Good night.
So Sathik, you are there from the beginning of the class. Sathik and Urvashi. Hello. Hello, Sathik, are you there? Sathik, Sathik Ahmed. Okay, guys, thank you.